Hello everyone, welcome to our YouTube channel, Calculus Hub UPI Cairo. In this video, we are going to cover Chapter 3 in Calculus 1 course. Title of this video is Limits and Continuity. I'm Hisham Hosni Hussein, Associate Professor of Applied Mathematics. Please prepare your notes, your pens, and let's go. Section 1, the concept of limits. In this section, limits asks simple question. As x approaches to some value, let's say a, what values does f of x get closer to? Here, we are not asking about the value of f of x exactly at this value x equals to a. Here, we are asking about the trend as we approaches this value a from both sides. Section 2, limits for piecewise functions. Most probably, real-life models switch rules. We can think of speed limits of routes, for example. For piecewise functions, limits look at the behavior near the switching point. Here, we check the left and right limits if they match, if they are equal, so the overall limit exists. Section 3, the computation of limits. In limits computations, we start by the direct substitution, but sometimes direct substitution fails. It gives 0 over 0, which is intermediate. This allows for algebra like factor and cancel common terms or rationalize the roots. The goal here is to simplify the expression to make the substitution doable again. Section 4, Sandwich Theorem. If you have a function g of x and this g of x is hard to analyze, but it's bounded between two simpler functions that squeeze or go to the same limit, then the g of x must go there too. In section 5, we are going to discuss limits at infinity and infinite limits. As x goes to a very large positive or very negative, what f of x approaches to? This is the first part. The second part, sometimes the function shoots up or down near a point. This is an infinite limit. In the last section, continuity, this is one of the aims of studying limits. Here, we will learn what is the meaning of continuity and the conditions for a function to be continuous. Section 1, the concept of limits. In this section, I want to illustrate the idea of limits with some simple example. Consider the following function, f of x equals to x squared minus 4 divided by x minus 2. This function is not defined at x equals 2. This means that we cannot substitute with x equals to 2. But usually we need to find important features about the behavior of such functions from its graph. So we can test its behavior in the neighborhood of this point, x equals to 2. We will compute some values for this function for x close to 2. At x is 1.9, the value of the function f of x is 3.9. X is 1.99, the function is 3.99. 1.999, so the value of the function is 3.999. At x equals to 1.9999, so this means that the function at this point is 3.9999 and so on. So with the approaching for x tends to 2 from the left, the value of the function is approaching to 4. Substituting with different values of x from the right, at x equals to 2.1, value of the function is 4.1. X 2.01, value of the function is 4.01. X is 2.001, value of the function is 4.001. At x 2.0001, value of the function is 4.1. Okay, this means that as we are approaching 2 from the right, the value of the function is approaching to 4. This can be clarified in the following graph. As we are approaching 2, as x is approaching 2 from the left, the value of the function is approaching to 4. This can be clarified in the following graph. As we are approaching 2 from the left, the value of the function is approaching to 4. As we are approaching 2 from the right, the value of the function is approaching 4 2. Okay, so this means that in the limit as x tends to 2 from the left, for the function x squared minus 4 divided by x minus 2, this equals 4. Similarly, this from x approaching 2 from the left. Similarly, as we clarified the limit for x approaching 2 from the right, for the function x squared minus 4 divided by x minus 2, this equals to 4 2. So this means that in the limit as x is approaching 2 for the function x squared minus 4 divided by x minus 2 equals to 4. Here we have another example for a piecewise function. We have a function g of x, and the g of x has two different definitions at the switching point 2. From the left of 2, the rule is different from the right of 2. Okay, We can start by the definition at x equals 2. Already the function here is not defined at x equals to 2. The function is defined at x equals to 5. So we can say that in here g of 5 equals to, it's clearly equals to 1. Here we are approaching 2 from the left. It's a 3. As we are approaching 2 from the right, it's 1. So this means that in the limit from the left does not equal to the limit from the right. So this means that in the limit for the function g of x as x is approaching 2 does not exist. Going to another point, find the limit as x is approaching to 5 from the left. We are approaching to the point, I think it's 2. This equals to 2. Limit for the function g of x as x is approaching to 5 from the right, it's 2. So the limit from the left equals to the limit from the right. Then the limit for this function g of x is 2 as x is approaching to 5. Use the graph of h in the figure to find the following values or state that they don't exist. Starting by h of 2, we need to find the value of the function h at x equals 2. At x equals 2, h equals to 5. B, find limit for the function h of x as x tends to 2. We need to find the limit from the left and from the right. Limit h of x as x tends to 2 from left. From left, the function is approaching this value. The function is approaching 3. This is from the left. Find the limit for the function h of x as x tends to 2 from the right. It will be 3, 2. So in general, limit as x tends to 2 for the function h of x, this equals to 3. C, find h of 4. H is not defined. There is no value for the function h of x at x equals to 4. So h of 4 is not defined. D, limit as x is approaching to 4. X is approaching to 4 from the left and from the right. Both are equal. They equals to this value, which is 1. So limit as x tends to 4 for the function h of x, this equals to 1. Limit as x is approaching 5 from the left and here from the right. The function is approaching to this value, which is 2. This is E. Limit h of x as x is approaching 5. This equals to this value, which is 2. In this exercise, given the function, this piecewise function, the function here has two different definitions. For x less than 2, the form of the function is 3 minus x. For x is greater than 2, the form of the function is half x. So we need to find the limit for this function as x is approaching to 2. Sketch the number line. This is the 2 on the number line. The value for the function for x less than 2 is 3 minus x. The form of the function for x is greater than 2 is half x. So find the limit for the function as x is approaching 2 from the left. Form of the function here is 3 minus x. And this equals to 1. Regarding limit as x tends to the value of 2 from the right, the form of the function is half x. Half times 2, this is 1, 2. So the limit from the right equals to limit from the left. Then limit for this function as x is approaching 2 from the left and from the right, they are equal. So at the end, limit for the function f of x as x is approaching 2 equals to 1. Assuming that we have the function f of x, this f of x is defined with more than one rule. For x is less than 0, the form of the function is x. For x is bounded by 0 and 2, the form of the function is x squared. For x is greater than 2, the form of the function is 8 minus x. And here we have several requirements. Let's start by redefine the function. Here the number line that's the function is defined on. This is 0. This is 2. Okay, for x less than 0, form of the function is x. For x is bounded by 0 and 2, and let's note that the function is not defined at 0. There is no equal at 0. For the function defined between 0 and 2, form of the function is x squared. For x is greater than 2, form of the function is 8 minus x. Now, let's start by finding the limit as x is approaching 1. As x is approaching 1, it's in the interval from 0 to 2. Then limit as x is approaching 1 for the function f of x. So here we replace f of x by x squared. Limit as x is approaching 1, x squared. This equals to 1 to the power 2, which is 1. The second question, double I. we need to find the limit as x is approaching to 0 from the left. This negative as a superscript means 0 from the left. So limit as x tends to 0 from the left for the function f of x is from the left, the form of the function is x. So limit as x tends to 0 from the left, it's x, this will be 0. Now we need to find the limit for the function f of x as x tends to 0 from the right. Limit as x tends to 0 from the right for the function f of x. This equals to limit as x tends to 0 from the right. Form of the function from the right of 0 is x squared. So just replace x by 0, you will get 0. This is the third requirement. Limit as x tends to 2 from the left. This IV limit for the function f of x as x tends to 2 from the left. Form of the function from the left of 2 is x squared. This equals to limit as x tends to 2 from the left. Form of the function is x squared. So this is 2 to the power 2, which is 4. V limit as x tends to 2 from the right. From the right of 2, form of the function is 8 minus x. This equals to limit as x tends to 2 from the right. It's 8 minus x. So it's simply 8 minus 2. This is 4, 2. Now let's go talking how to compute limits. Actually, if we have limit for some function f of x as x tends to a, we use the direct substitution. If you use the direct substitution, here we have two scenarios. We may get some value k, which is fine, this is the value of the limit, or we may get intermediate form like 0 over 0. And here it's a problem. We need to identify the specific value of the limit. So if we get limit for some function f of x as x tends to some value, and the result, what we get from this limit is 0 over 0. So here we have three scenarios. The first, second, and the third. The first scenario is factor, then cancel the zero factor. This is the first scenario. The second scenario is multiply by the conjugate. If we have some constant minus root, if we have root minus root, another root minus root, here this is the proper form for using the multiplication by the conjugate technique. Or use the identity that limit as x tends to 0, the sum x divided by x, this equals to 1. Or if we have limit as x tends to 0, sine kx divided by x, this equals to k. Another alternative formula, if you have limit as x tends to 0 for 10 kx divided by x, this equals to k2. Here, these are the three forms that we use if we have a trigonometric function in the limit. Sine, 10, 1 minus cosine, and so on. Starting by this limit, limit as x tends to negative 2 for 3x power 4 plus 2x squared minus x plus 1. So just replace each value of x. So just replace each x by negative 2. It's 3 multiplied by negative 2 to the power 4 plus 2 times negative 2 to the power 2 minus negative 2 plus 1. Here it's 16 times 3, this is 48 plus 4 times 2, this is 8, plus 2 plus 1. So this 54 plus 1, which is 55. What if we have like this limit? Limit as x tends to 2, x squared plus x minus 6 divided by x minus 2. Direct substitution, replace each x here by 2. So it's 4 plus 2 minus 6 divided by 2 minus 2. You will get 0 divided 0. Okay, so it's clear here that the numerator is a second degree polynomial. So let's check if we can factorize this polynomial or not to cancel the zero factor, the factor that leads to 0. So factorizing here, the second degree polynomial, it will be x plus 3 times x minus 2. And already in the denominator, we have x minus 2. So I think it's clear that we can simplify, we can cancel this x minus 2 with this x minus 2 to get limit as x tends to 2 for the remaining factor x plus 3. This is 2 plus 3, which is 5. In this problem, limit as t tends to negative 3. In the numerator, we have t squared minus 9 divided by 2t squared plus 7t plus 3. So direct substitution, replacing t by -3, you will get 9 minus 9 in the numerator, divided by, in the denominator here, it's 9 times 2, this is 18, minus 21, plus 3. So you will get 0 divided 0. 0 divided 0, and we have polynomial in the numerator and polynomial in the denominator. So let's try with factorizing the numerator and denominator to cancel the zero factor. Limit as t tends to -3. In the numerator, we can factorize this t squared minus 9 to be t minus 3 times t plus 3. Regarding the polynomial in the denominator, we can factorize it to be 2t plus 1 times t plus 3. Already here, the zero factor is clear, which is t plus 3. So we can cancel t plus 3 up and down to get limit as t tends to -3. In the numerator, we have t minus 3. In the denominator, we have 2t plus 1. So now, try with the direct substitution. You will get -3 minus 3 divided by -6 plus 1. -3 minus 3, this is -6, divided by -1. For this limit as h tends to 0, in the numerator, we have 2 plus h power 3 minus 8. This is divided by h. Okay, so here we have 2 plus h power 3. We have a plus b power 3. This equals 2. The first term will be a power 3. The second term will be 3 times this a square times b. The third term is 3 times 1a times b square. The fourth term is b power 3. So we can follow the same and write this 2 plus h power 3 using this form. The first term will be 2 power 3, which is 8. The second term will be 3 times 2 squared, which is 4, times h, plus. The third term will be 3 times 2 times h squared. It's 3 times 2 times h squared, like this one. 3 times the first term times the second one squared, plus the h power 3. Now, simplify. It's 8 plus 12h plus 6h squared plus h power 3. Now, substitute with this expression with 2 plus h power 3. Then limit as h tends to 0. In the numerator, we have replace this 2 plus h power 3 with this expression. It's 8 plus 12h plus 6h squared plus h power 3 minus 8. This is divided by h. So I think it's clear that we can cancel this 8 with this -8. And we can factor h from the numerator. So to get limit as h tends to 0. We can factor h from the remaining factors. Here we have h squared, h power 3. So we can take h as a common factor to get 12 plus 6h plus h squared divided by h. Now we can factor h and then replace h here by 0 to get at the end 12. This is the value of the limit. Here we have limit. In problem 6, we have limit as t tends to 9 for 9 minus t divided by 3 minus root t. Direct substitution, you will get 0 divided by 0. Okay, so what should we do at this step? Here we have limit as t tends to 9. In the numerator, we have 9 minus t, which is a 0 factor. In the denominator, we have 3 minus root t, which is another 0 factor in the denominator too. So multiply by what's called conjugate for this 3 minus root t. What's the form of this conjugate? It's 3 plus root t, 3 plus root t. This is the same as you multiply by 1. 3 plus root divided by 3 plus root, this is 1. Okay, this equals to limit as t tends to 9. In the numerator, we don't have any trick, so just multiply the factors. 9 minus t, which is multiplied by 3 plus root t. In the denominator, it's different. Here we have 3 minus root t times 3 plus root t. This is the same as the difference between two squares. It's a 3 power 2 minus root t power 2. Root t power 2 is t. 3 power 2 is 9. Okay, so this means that we get 9 minus t in the denominator and 9 minus t in the numerator. So we cancel 9 minus t, which is the 0 factor, from the numerator and the denominator to get limit as t tends to 9, 3 plus root t. Now t is approaching to 9, so it's a 3 plus root 9. Root 9 is 3. So this 3 plus 3, which is 6. Another problem here, we have limit as x tends to 9 to x squared minus 81 divided by root x minus 3. Direct substitution, this is 0 over 0. Then the limit as x tends to 9. In the numerator, we have x squared minus 81. In the denominator, we have root x minus 3. And this root x minus 3 is a 0 factor. So just multiply the conjugate for this 0 factor, root x minus 3. Its conjugate is root x plus 3 divided by root x plus 3 to get limit as x tends to 9. In the denominator, we have root x minus 3 times root x plus 3. Here, root x times root x, this is x minus 3 times 3, this is 9. So we have in the denominator here x minus 9. In the numerator, we have x squared minus 81, which contains a 0 factor. Here, this root x plus 3 as it is. Okay, x squared minus 81. This x squared minus 81 can be factored to be x minus 9 times x plus 9. And this x minus 9 is a 0 factor. As x here is approaching to 9, just replace x by 9, you will get 0 in the numerator and you will get 0 in the denominator. Canceling this x minus 9 with this x minus 9. Okay, so we will get, after canceling the 0 factor, limit as x tends to 9. In the numerator, it's x plus 9 times root x plus 3. That will be 18, which is 9 plus 9. It's 18 times 6, which is some value you can calculate. Here we have the limit x tends to 1 for root x minus x squared divided by 1 minus root x. By the direct substitution, you will get 1 minus 1 divided by 1 minus 1. That will be 0 divided 0. As here we have root in the numerator and another root in the denominator, so we will apply the idea of multiplying by the conjugate up and down. Limit as x tends to 1, root x minus x squared divided by 1 minus root x. The conjugate of the numerator is root x plus x squared divided by root x plus x squared. Conjugate of the denominator is 1 plus root x divided by 1 plus root x. So, root x plus x squared, when it's multiplied by root x minus x squared, we will get limit as x tends to 1. Root x times root x, it's x. X squared times x squared is x to the power 4 divided by. We have 1 minus root x. If we multiply it by 1 plus root x, its conjugate, we will get 1 minus x times root the remainders, root x plus x squared and 1 plus root x in the numerator. It's multiplied by 1 plus root x divided by root x plus x squared. They are not 0 factors, by the way. But still here we have a problem with x minus x to the power 4 divided by 1 minus x. So limit as x tends to 1. Factor x from the numerator, we will get x times 1 minus x power 3. In the denominator, already we have 1 minus x times the other fraction, which is limit as x tends to 1, 1 plus root x divided by root x plus x squared. We can simplify this. Here, this is 1. Just replace x by 1. It will be 1 plus 1 divided by 1 plus 1. So it's 2 divided 2, which is 1. Okay, so now we have another fraction, which is limit. This is the main limit. Limit as x tends to 1 for x times 1 minus x power 3 divided by 1 minus x. So we can factor 1 minus x power 3. We'll get limit as x tends to 1. X times. Factoring this 1 minus x power 3, you will get 1 minus x times 1 plus x squared divided by 1 minus x. Now this is the appearance for the 0 factors. 1 minus x, and here we have 1 minus x. We can cancel them. To get at the end, replace each x now by 1. 1 plus 1 plus 1, it's a 3. 3 times 1, it's 1 multiplied by 3, so it's 3 at the end. The limit for this function, limit as x tends to negative 2. X plus 5, okay, multiplied by absolute x plus 2 divided by x plus 2. So already we defined before the absolute value, if we have absolute for whatever. So this means that in this absolute will be what's inside absolute as it is if this was positive, and it will be negative for what's inside absolute if it was negative. So here, let's go redefining this x plus 2, as I think that I guess there will be a problem here. From the direct substitution, you can detect that in here we have negative 2 plus 5, this is 3, and this 3 is multiplied by 0 divided 0, as I told you, which is intermediate value. Let's redefine the absolute of x plus 2. Absolute of x plus 2 will be x plus 2 as it is, or it will be negative x plus 2. It will be x plus 2 if this x plus 2 was positive, or it's negative x plus 2 if it's negative. It will be negative x plus 2 if it's negative, if this x plus 2 is negative. Redefine the absolute again, rewrite it. It's x plus 2 if this x greater than negative 2, or it's negative x plus 2 if this x less than negative 2. Okay, so this is the redefinition for absolute x plus 2. Okay, now this means that so we can detect that there are two definitions for this function before negative 2 and after negative 2. If x is greater than negative 2, to the right of negative 2, it will be x plus 5 times x plus 2. As we are greater than negative 2, it will be x plus 2 as it is, x plus 2 divided by x plus 2. X plus 2 divided x plus 2, it will be 1. So this is the resulting factor, x plus 5. For x less than negative 2, for x less than negative 2, the form of the function will be x plus 5 times, replace the absolute by negative x plus 2 divided by x plus 2. So by canceling this x plus 2 and this x plus 2, we will get negative 1. At the end, we will get negative x plus 5. So this means that we have two different forms for the function. From the left is different from the right. Okay, so find the limit from the left and from the right. Limit as x tends to negative 2 from the left. Form of the function from the left is negative x plus 5. So it will be negative 2 plus 5, this 3, it's negative 3. And limit as x tends to negative 2 from the right. For the function from the right, it's x plus 5. This is simply 3. So value of the limit from the left is not equal to the value of the limit from the right, which means that in the limit for this function as x tends to negative 2 does not exist. Find the limit for this function. Here limit as x tends to 0 for root x plus 1 minus 1 divided by root x plus 4 minus 2. Direct substitution, you will get 0 divided 0. Here we have two roots, so multiply by the conjugate up and down. Limit as x tends to 0. We have root x plus 1 minus 1 divided by root x plus 4 minus 2. Multiply by the conjugate of the numerator. It's root x plus 1 plus 1 divided by root x plus 1 plus 1 times conjugate of the denominator, root x plus 4 plus 2 divided by root x plus 4 plus 2. So its limit as x tends to 0. Root minus 1 multiplied by root plus 1. And root minus 2 multiplied by root plus 2. This will be root x plus 1 minus 1 times root x plus 1 plus 1. It will be x plus 1 minus 1 divided by root x plus 4 minus 2 when it's multiplied by root x plus 4 plus 2. It will be x plus 4 minus 2 squared, which is 4, times root divided root. The remainders. Limit as x tends to 0, root x plus 4 plus 2 divided by root x plus 1 plus 1. And I think that we can substitute. It's 2 plus 2, you will get 4 divided by 1 plus 1, you will get 2. So replace this fraction by 2. Replace this factor by 2. You can directly replace this limit by 2 after substitution with 0. Now, in the main limit, cancel negative 1 and 1, cancel 4 and the negative 4, you will get x divided x, which is 1. So the value of the limit will be 1 times 2, which will be 2. Okay, now for this limit, x tends to 0, 2x power 3 divided by 10 to the power 3 to x. By the direct substitution, you will get 0 divided by 0. This is step 1. Step 2, you can factor 2 out of this limit to write it as 2 limit as x tends to 0 for x power 3 divided by 10 to the power 3 to x. Okay, here we can use the rules of the limit that we stated at the beginning of this section. How come? Already we can rewrite this factor to be 2, don't forget, limit as x tends to 0, and represent this x power 3 to be denominator of the denominator. It will be 1 divided by 10 to the power 3 to x divided by x power 3. This first. Second, to limit, this is the first action, to limit as x tends to 0 for rewrite this 10 power 3 divided by x power 3 as 10 to x divided by x all to the power 3. So now we can write the limit as 2 divided by limit as x tends to 0 for 10 to x divided by x all to the power 3. But already we know that in limit as x tends to 0 for 10 kx divided by x, this equals to k. So just replace this 10 to x by x with its limit as tends to 0, just replace it by 2. So you can write it at the end as 2 divided by 2 to the power 3. So you can write it as 2 divided by 2 to the power 3, which is 1 over 4. Here we have limit as x tends to 0 for 1 minus cosine x divided by x. Direct substitution for this limit, you will get 1 minus 1 divided by 0, which is 0 divided by 0. I know that already we have a trig function in the numerator, but actually we don't have a specific formula for cosine divided by x as we have limit. As we have limit as x tends to 0, sine x divided by x equals to 1, we don't have a similar formula for cosine. But already we know that in 1 minus cosine squared x equals to sine squared x. So we can create 1 minus cosine x here in this limit. How come? Here we have limit as x tends to 0. In the numerator, we have 1 minus cosine x divided by x. So just multiply the numerator by 1 plus cosine x, and we will do the same for sure in the denominator, 1 plus cosine x. The aim from this action is, here we have 1 minus cosine x times 1 plus cosine x, difference between two squares, which is 1 minus cosine square x, divided by x times 1 plus cosine x. So 1 minus cosine squared can be replaced by sine square x. So we can rearrange the factors that we have. We have now limit as x tends to 0. We have sine x divided by x times sine x, as in we have now sine squared, times 1 over 1 plus cosine x. So this will be limit as x tends to 0 for sine x divided by x times limit as x tends to 0 for sine x times limit as x tends to 0 for 1 over 1 plus cosine x. Here, the value of this limit is half. You can just replace x by 0. Cosine 0 is 1, 1 plus 1 is 2. Here, sine 0 is 0. Here, limit as x tends to 0 for sine x divided by x, this is 1. So we have a product of 1 times 0 times half. This would be 0 at the end. In this problem 13, we have limit as x tends to 0 for x power 3 minus 2 10x divided by x. Don't forget that we have the identity limit as x tends to 0 for 10x divided by x. This equals to 1. So we can, at the beginning, for sure, direct substitution, you will get 0 over 0. So we can split this limit into two limits. Limit as x tends to 0. X power 3 divided by x minus 2. Limit as x tends to 0. 10x divided by x. Limit as x tends to 0. 10x divided by x. This is 1. Limit as x tends to 0 for x power 3 divided by x. This is x squared. Now the value of the first limit is simply 0. Minus 2 times 1, which is negative 2. Now in section 4, the sandwich theorem. The sandwich theorem is stating that if we have g of x, if we have some function g of x and the g of x was bounded by two functions, f of x and h of x, and the limit as x tends to some value for f of x was equals to the limit as x tends to the same value for h of x, if they are equal, for example, equals to some value, let's say L, then the limit for this middle function as x tends to a, g of x, this equals to L2. The question here is, who want to use the sandwich theorem? We use the sandwich theorem with bounded functions. For example, like sine for whatever is bounded by negative 1 and 1. The same for cosine. Cosine for any input is bounded by negative 1 and 1. Tan inverse. Tan inverse for whatever is bounded by negative pi over 2 and pi over 2. And the same for its square. We have sine square for whatever. We have cosine square for whatever. If we have absolute sine, if we have absolute cosine. So with these functions, we can use the sandwich theorem. And the same if we have tan inverse for some function square. It's bounded by 0 and by over 2 square. We have the absolute value for tan inverse. It's bounded by 0 and by over 2. Here in this function, we have x sine x divided by 2 times 1 minus cosine x. This function is bounded by another two functions. Constant function, which is 1, and another function, which is 1 minus x squared divided by 6. So it's requested to find the limit for the in-between function, which is x sine x divided by 2 times 1 minus cosine x. So we find the limit for the h and f functions. Limit as x tends to 0 for 1 minus x squared divided by 6. This will be 1. And the limit for the other boundary, which is limit as x tends to 0. For its constant function, it's 1. So its limit will be 1. So this means that in the limit for the in-between function, x tends to 0, x sine x divided by 2 times 1 minus cosine x. This is 1, 2. Here we have limit as x tends to 0, x squared times cosine 20 pi x. Already cosine for any argument is bounded by negative 1 and 1. So here it's bounded by negative 1 and 1. Now multiply by x squared to create the requested function. So it's negative x squared bounded by x squared cosine 20 pi x less than or equal to x squared. Now find the limit as x tends to 0. Here we need to find the limit as x tends to 0. So find the limit as x tends to 0 for negative x squared and x squared. Okay, limit as x tends to 0 for negative x squared is 0. And it is equal to limit as x tends to 0 for x squared. So limit for the in-between function, which is x squared cosine 20 by x, this equal to 0 too. It's requested to find the limit as x tends to 0 for absolute cosine x divided by x. Here, absolute cosine x is bounded by 0 and 1. But here we have absolute cosine x divided by x. So divide by x for the three sides. Then 0 divided by x, it's 0, less than or equal to absolute of cosine x divided by x less than or equal 1 divided by x. Now it's requested to find the limit as x tends to infinity. Already this is 0. What about the limit here? The limit as x tends to infinity, the requested one, for 1 over x is 1 over infinity, which is 0. So the limit for this boundary is 0. It's already a constant function. The limit for the other boundary is 0. Then limit as x tends to infinity for the intermediate function cosine, absolute cosine x divided by x, it will be 0. It's requested to find the limit for root x power 3 plus x squared times sine pi over x as x tends to 0. Already sine pi over x is bounded by -1 and 1. So to create the requested function, just multiply by root x power 3 plus x squared. Then we get negative root x power 3 plus x squared less than or equal root x power 3 plus x squared times sine pi over x to be less than or equal root x power 3 plus x squared. So now find the limit for the boundaries as x tends to 0 for negative root x power 3 plus x squared. This will be 0. The same limit as x tends to 0 for the other boundary, limit as x tends to 0 root x power 3 plus x squared. This will be 0. So at the end, the limit for the requested function will be 0. Find the limit as x tends to infinity for tan inverse ln x divided by x as x tends to infinity. Already we know that in tan inverse for whatever is bounded by negative pi over 2 and pi over 2. So here tan inverse ln x, it's bounded by, it's greater than negative pi over 2 and it's less than pi over 2. Divide by x for both sides, you will get to create the requested function tan inverse ln x divided by x less than pi over 2 divided x, and it would be greater than negative pi over 2 divided x. Now find the limit for the boundaries, limit for negative pi over 2 divided x and limit for pi over 2 divided x. So limit as x tends to infinity for negative pi over 2 for negative pi over 2 divided x, which is negative pi over 2 divided infinity. This is 0. Division of any constant over infinity, it's 0. And the same limit as x tends to infinity for pi over 2 divided x. This is 0 too. So the limit for the requested function tan inverse ln x divided by x, it's 0. Now in section 5, infinite limits and limits at infinity. Starting by the first part, infinite limits. We have a limit for some function f of x, and this x is approaching to some value a, maybe this a2, 0, 5, whatever. So we get infinity or negative infinity. This is the form of the infinite limits. Do we have examples for this? Yes. If we have limit as x tends to 0 for 1 divided by x squared. The sketching of 1 divided by x squared is as we approaching 0 from the right, we go to infinity. If we are approaching 0 from the left, we go to infinity too. So the limit for 1 divided by x squared is infinity. Another form, limit for 1 over x. As you know, 1 over x is hyperbolic shape in the first and the third equations. Limit as x tends to 0 from the right tends to infinity. But limit as x tends to 0 from the left, we goes to negative infinity. So limit for 1 over x as x tends to 0 from the right, this is infinity. Limit as x tends to 0 from the left, for the same function 1 over x, we get negative infinity. Infinity and negative infinity for the same limit. So limit as x tends to 0 for the function 1 over x does not exist. And here, this y-axis will be called vertical asymptote. And the same here for 1 over x, this y-axis will be vertical asymptote. Now going to the second part of this section, which is the limit at infinity. Limit as x tends to infinity for some function. Already we know forms. We have limit as x tends to infinity for the function 1 over x. Here, it's 1 over x. As x tends to infinity, the function is approaching to 0. As x tends to negative infinity, the function is approaching to 0 too. So here, limit as x tends to infinity for 1 over x, the 0, the same limit as x tends to negative infinity for 1 over x, this is 0 too. And here, this x-axis would be called horizontal asymptote. Thinking about the function, limit as x tends to infinity for 1 over x squared. This is the sketch of 1 over x squared. As x tends to infinity, we are approaching 0. As x tends to negative infinity, approaching 0 too. So the limit as x tends to infinity for 1 over x squared is 0. Limit as x tends to negative infinity for 1 over x squared, this is 0 too. Different type of functions like the exponential functions. Different types of functions like the exponential functions. Here we have e to the power x. E to the power x. As we are approaching infinity, as we goes to infinity with x, the function itself goes to infinity. As we are approaching negative infinity, the function itself approaching to 0. So limit as x tends to infinity for e to the power x, it's infinity. But limit as x tends to negative infinity for the same function e to the power x, this equals to 0. What if we have e to the power negative x? Here, limit as x tends to infinity, this e to the power x and this e to the power negative x. As x tends to infinity for this e to the power negative x, here we are approaching infinity. So the function here approaching to 0. While limit as x tends to negative infinity for e to the power negative x, here we are approaching to negative infinity. So the function here is approaching to infinity. Another function like len, y equals to len x. Limit as x tends to infinity for len x. We are approaching infinity. So the function itself, x here is approaching infinity. So the function itself is approaching to infinity. This equals to infinity. By the way, if we have limit as x tends to 0 from the right, the function here has no definition from the left. If we are talking about the limit as x is approaching 0 from the right, for the function len x, this equals to negative infinity. Now the question is, what if we have limit as x tends to plus or minus infinity for a polynomial p of x divided by another polynomial q of x, and the value of the limit equals to infinity divided infinity, one of the intermediate values. The same if we have limit as x tends to plus or minus infinity p of x minus q of x, and we get one of the another intermediate value, which is infinity minus infinity. So how can we deal with this? We have limit x tends to plus or minus infinity p of x divided by q of x. Here we have a polynomial in the numerator and another polynomial in the denominator. Step 1, identify the degree of the denominator. So step 1, identify the degree of q of x. What's the meaning of the degree of the q of x? What's the meaning of this expression, degree of q of x? Degree of q of x means that the highest power of x in q. We have x power 3 plus x squared, so x power 3 is the highest power. Let's say that it's x to the power m. The step 1. Divide by this x to the power m that you found, divide by x to the power m up and down. So if you have limit as x tends to plus or minus infinity, whatever, so p of x divided by x to the power m divided by q of x, which is divided by x to the power m. Simplify using the identity that in the limit as x tends to plus or minus infinity for k divided by x to the power n is 0, where this n is greater than 0. This n have to be positive. Now start our training with the limits as x tends to infinity. Limit as x tends to infinity for 3x squared minus 6x plus 4 divided by x power 3 plus 2. Direct substitution, you will get infinity divided by infinity. So the highest power in the denominator is x power 3. This means that we will divide by x power 3 up and down. So limit as x tends to infinity in the numerator, it's 3x squared divided by x power 3 minus 6x divided by x power 3 plus 4 divided by x power 3 is divided by x power 3 divided by x power 3 plus 2 divided by x power 3. Okay, now x power 2, sorry, x power 2 divided by x power 3, this is 1 over x. This is 1 over x. You will find the limit for this 1 over x. X divided by x power 3, this is 1 over x squared. You will find the limit for this 1 over x squared. 3 divided by x power 3, you will find its limit 2. X power 3 divided by x power 3, this is 1. 2 divided by x power 3, you will find it. Okay, now limit for 1 over x as x tends to infinity is 0. 1 divided by x squared, its limit is 0, 2. 4 divided by x power 3, it's 0. 2 divided by x power 3, it's 0, 2. So the value of this limit is 0 divided by, here we have 1 plus 0, it's 1. So it's 0 at the end. Problem 2. Here we have limit as x tends to infinity. 7x squared plus 9x plus 2 divided by 2x squared plus 1. Direct substitution, you will get infinity divided infinity. Highest power in the denominator, it's x power 2. So divide by x power 2 up and down. You will get limit as x tends to infinity. In the numerator, we have 7x squared divided by x squared plus 9x divided by x squared plus 2 divided by x squared. It's divided by 2x squared divided by x squared plus 1 divided by x squared. Now simplifying x squared divided x squared, this is 1. X divided x squared, this is 1 over x. Here x squared divided x squared, this is 1. Now find the limit. Here we have 1, find the limit for 1 over x, find the limit for 2 over x squared, limit for 1 over x squared for 1. So it will be in the numerator 1 times 7, this is 7, plus 1 over x, its limit is 0. 2 over x squared, its limit is 0, divided by 2 times 1, it's 2, plus 1 over x squared, its limit is 0. So the limit here is 7 over 2. Here we have 3x power 4 plus 2x plus 1 divided by x squared plus 5 as x tends to infinity. Direct substitution, infinity divided infinity. Highest power in the denominator, x squared. So divide by x squared up and down. You will get limit as x tends to infinity. In the numerator, we have 3x power 4 divided by x squared plus 2x divided by x squared plus 1 divided by x squared. In the denominator, it's x squared divided by x squared plus 5 divided by x squared. X divided by x squared, it's 1 over x. X power 4 divided by x power 2, it's x power 2. X squared divided by x squared, it's 1. So you will find the limit for x squared, you will find the limit for 1 over x, for 1 over x squared, for 5 divided by x squared, and for 1. So this will be 3 times infinity squared, it's infinity. Infinity times 3, it's infinity. Infinity plus, this is 0, plus another 0, divided by 1 plus 0. So the limit at the end is infinity. Find the limit for x plus 1 divided by 2x squared plus x plus 1 as x tends to negative infinity. Direct substitution, you will get negative infinity divided by infinity, which is one of the intermediate forms. Dividing by x squared, the highest power in the denominator, up and down. So this will be limit as x tends to negative infinity. Now divide by x squared. It's 2x squared divided by x squared plus x divided by x squared plus 1 divided by x squared. Here in the numerator, x divided by x squared plus 1 divided by x squared. Now simplify. X divided x squared, it's 1 over x. X squared divided x squared, it's 1. X divided x squared, it's 1 over x. So now it's time for simplification and for evaluating the limit directly. 1 divided negative infinity, it's 0. 1 divided infinity, it's 0, 2. Here already we have 1 which is multiplied by 2, 0, and another 0. So this will be 0 plus 0 divided by 2 plus 0 plus 0, which is 0. Now here we have root in the numerator. Applying the direct substitution as usual, so you will get infinity divided infinity. So what should we do here? Find the highest power of x in the denominator, which here is x power 2. So divide by x power 2 up and down. Now limit as x tends to infinity. In the denominator we have 5x squared divided by x squared plus 9 divided by x squared. In the numerator we have this root that will be divided by x squared, 2x power 4 plus 2x. This is divided by x squared minus 1, which is divided by x squared. I can rewrite this x squared as root x power 4. Why to do this? This to unify the denominator. Unify. Why to do this? This to unify the fraction. So the limit here will be limit as x tends to infinity. In the numerator we have root 2x power 4 divided by x power 4. After writing it as root x power 4, you will get 2 plus 2x divided by x power 4 minus 1 over x squared, 5x squared divided x squared plus 9 divided x squared. Already x divided x power 4, we can replace it by 1 divided x power 3. X squared divided x squared, already we did it before, it's 1. Then we have 1 divided x power 3, we have 1 divided x power 2, 9 divided x power 2, and 1. So the final value of this limit will be, here it's 0, 0, minus 0, 0, 2. So it's root 2 divided 5. Regarding this limit, here we have negative x squared plus x plus 1 divided by x plus 1. By the direct substitution here, you will get negative infinity minus infinity divided by negative infinity, which is infinity divided infinity, intermediate value. So divide by the highest power in the denominator, which is x. Divide by x up and down. Limit as x tends to negative infinity. Divided by x in the denominator, you will get x divided x plus 1 divided x. Divided by x in the numerator, it's negative x squared divided x plus x divided x plus 1 divided x. X divided x will be replaced by 1. Negative x squared divided x will be replaced by x. It's negative x. It's negative x. X divided by x will be replaced by 1 too. So the answer will be negative x plus 1 plus 0. Here, the denominator here, 1 over x, we have another 0. So negative x, and replace this x by negative infinity, it's infinity plus 1 divided by 1 plus 0. Already here we have 0. So it's infinity at the end. Limit as x tends to infinity for root x squared plus 4 minus x. Direct substitution, you will get infinity minus infinity. So what should we do here? Multiply by the conjugate as usual. So limit as x tends to infinity. Root x squared plus 4 minus x multiply by root x squared plus 4 plus x divided by root x squared plus 4 plus x. We will get, after multiplying by the conjugate, limit as x tends to infinity, root times root, you will get x squared plus 4 minus x times x, it's x squared, divided by root x squared plus 4 plus x. Now cancel this x squared with this one to get 4 at the end. Already now we have 4 divided by root x squared plus 4. Let's write it. Limit as x tends to infinity. We have now 4 divided by root of x squared plus 4 plus x. This will be 4 divided by infinity power 2 is infinity. Infinity plus 4 is infinity. Root infinity, it's infinity. Infinity plus another infinity, it's 2 infinity, which is infinity. So it's 0 at the end. Limit as x tends to infinity for e to the power 3x plus 4 divided by e to the power 3x plus 5. Direct substitution, you will get infinity divided infinity. The dominant function in the numerator is e to the power 3x, and the same in the denominator, e to the power 3x2. So we can divide by e to the power 3x up and down. Now going to the last section in this chapter, which is the continuity of functions. The definition for the continuity of functions that's defined in the textbooks is A function is said to be continuous on some interval if its graph on this interval can be sketched without any interruption, without any cutting. This means that you will sketch this function without lifting your pencil from the paper, like this one. Here we have a hole at x equals to a. Here the function from the left does not equal, the limit from the left does not equal to the limit from the right. So here these are two examples for the not continuous functions. Okay, so the formal definition for a function to be continuous at some point, the limit equals to the definition of the function. The limit from the left and from the right equals to the definition of the function. This is the formal definition. A function is said to be continuous at some point if the following conditions are satisfied. F of a is defined, which means that the function has a value at x equals to a. This is the first condition. The second one is the limit exists. The third one is the limit equals to the definition. The second condition, the limit equals to the definition, which is the first condition. In the shown figure, this graph for some function f has three problems. The first one, at x equals to 1, the function is not defined at x equals to 1. So the function here is not continuous at x equals to 1. The second problem with the continuity for this function is at x equals to 3. The limit from the left at x is approaching to 3 is not equal to the limit from the right as x is approaching 3. The third problem at x equals to 5. The limit, already here the limit exists at x is approaching 5 from the left and from the right, but the value of the limit does not equal to the definition of the limit at x equals to 5. Discuss the continuity for the following functions at all values of x. Okay, here sketch the number line like this one. We have two switching points at 0 and at 1. At the beginning, when x is less than or equal to 0, the form of the function is x plus 2. In the interval from 0 to 1, the form of the function is 2x squared. For x is greater than 1, the form of the function is 3 minus x. At 1, the function is open, so the function is not defined at x equals to 1. We don't have any equality here at 1, so the function is not continuous at x equals to 1. At 0, the function is closed, and the definition of the function when x equals to 0 is x plus 2. So f of x is, so now going to discuss the continuity first at the switching points at x equals to 0. At x equals 0, find the limit. Limit as x tends to 0 from the left, form of the function is x plus 2. So it's 2. Limit as x tends to 0 from the right, form of the function is 2x squared. So it's 0. Limit from the left does not equal to the limit from the right. So the limit for the function f of x as x approaching to 0 does not exist. This means that then f of x is not continuous. F of x is not continuous at x equal to 0. It's at x equal to 0. What about this at x equal to 0? What about at x equals to 1? At x equals to 1, f of 1 is not defined. So f of x is continuous on the intervals from negative infinity to 0 open, union from 0 to 1, union from 1 to infinity. Here in this exercise, it's given that in this function is continuous. And as in this function is continuous, we need to find the value of the unknown constant c. Since f of x is continuous, so this means that in f of x is continuous at x equals to 4. Then limit f of x as x tends to 4 exists, which means that in the limit as x tends to 4 from the left, x squared minus c squared equals to the limit as x tends to 4 from the right, cx plus 20. So now evaluate the left hand side, it's 16 minus c squared. Evaluate the right hand side, it's 4c plus 20. So now c squared, transform it into 0 quadratic equation, c squared plus 4c plus 4, this equal to 0. Solving it on the calculator, you will get that in c equals to negative 2.